Welcome to Math Zone African Motives. In today's tutorial, we're diving into the fundamental concepts of torque, work done, and power. By the end of this video, you will be able to calculate these quantities for rotational motion. Our goal is to make these concepts clear, step by step, with practical examples. We'll begin with the first concept, torque. The moment of a force, or torque, is the energy transferred to an axis by a force. It's calculated by multiplying the force's magnitude and its perpendicular distance from the turning point. So we can write the moment of F about point O as F times R. Let's define some key terms. First, we have torque. Torque is the tendency of a force to rotate an object. It causes rotation. The pivot is the center of the shaft, while the fulcrum is the support point for a lever. Visually, think of a spanner. The force you apply to the handle creates a torque that tightens the nut. Torque, represented by the letter T, is the force F multiplied by the perpendicular distance R. It measures the turning effect of a force. In this scene, we've defined torque and the formula to calculate it. You can now define and calculate the torque caused by a force. Next up is work done by torque. Our objective here is to derive the formula for work done during rotation. We know that for linear motion, work done W equals force F times distance S. This is the definition of work. Let's apply this to one full revolution of a shaft with a radius r. For one revolution, the distance s is the circumference of the circle, which is pi times the diameter d, or 2 pi times the radius r. So the work done in one revolution is force F times 2 pi. Now let's rearrange this formula. We can group the F and the r together. Remember our previous formula for torque? T equals F times r. This means we can substitute T into our work equation. And there we have it. The work done for one revolution is 2 pi times the torque, T. This is a crucial formula for rotational work. We have now derived and understood the work done by torque. Our next goal is to connect work done and torque with a new concept, power. The definition of power, P, is the rate at which work is done. It's calculated by dividing the work done W by the time T. For rotational systems, there's another very useful formula for power. Let's derive it. We know work done for one revolution is W equals 2 pi t, and power is work over time, so P equals 2 pi t over t. Now let's look at the term 1 over t. The time t here is the time for one revolution. The inverse of the time for one revolution is the number of revolutions per second, or the frequency, which we denote as n. By substituting n for 1 over t, we get the rotational power formula, P equals 2 p and t. This relates power directly to the torque and the speed of rotation. So we've successfully connected these concepts and learned how to calculate power. Now let's tackle our first example. The objective is to calculate the torque, work, and power when a force is applied at an angle. The question states, a force of 400 newtons is applied to the end of a spanner. The force makes an angle of 60 degrees with the spanner. The length of the spanner from the center of the nut to the point of application is 0.25 meters. Calculate the torque, the work done for a 70-degree turn, and the power if the motion takes 0.5 seconds. First, let's list our given values. The force F is 400 newtons. The distance from the pivot, or radius r, is 0.25 meters, and the angle is 60 degrees. The most important thing to remember when calculating torque is that we need the force perpendicular to the spanner. We cannot use the full 400 Newton. Let's draw this. Here is the spanner. Here is the total force, F, at 60 degrees. We need to find the component of this force that is at 90 degrees to the spanner. This component will cause the rotation. Looking at the provided solution, it uses an angle of 30 degrees. This is because the solution is calculating the force component along the vertical axis, not the component perpendicular to the spanner directly. Let's find out why. The angle between the horizontal spanner and the vertical force component is 30 degrees. This is the complement of the 60-degree angle, since they add up to 90 degrees. The side adjacent to the 30-degree angle is the vertical component. Using trigonometry, this side is F times the cosine of 30 degrees. So the perpendicular force is 400 times cos 30, which is approximately 346,041 newtons. An alternative, and perhaps more direct method, is to use the 60-degree angle given in the problem. Using the 60-degree angle, the perpendicular force is the side opposite to it. The opposite side is calculated as F times the sine of 60 degrees. 400 times sin C also gives 346,041 newtons. Both methods lead to the exact same perpendicular force, which is the force that causes rotation. It seems there was a typo in the provided diagram, labeling the force component as F cos 30. Let's correct this on the diagram for clarity. The diagram should correctly show the perpendicular component as F sine of 60 degrees. This component is 346.41 newtons. Now we can solve part A, the torque. The torque, T, is the perpendicular force, which we've found to be 346.41 newtons, multiplied by the radius r, which is 0.25 meters. This gives us a torque of 86.6025 newton meters. The memo rounds this to 86.603 newton meters. So, the torque is the perpendicular force times the radius. We have now solved for torque, the first part of our objective. Now let's continue with part B and C of example 2.5. The formula for work done by a constant torque through an angle is T dot theta. Here T is the torque and theta is the angle in radians. First, we need to convert the angle of 70 degrees into radians. The conversion factor is pi radians equals 180 degrees. So, 70 degrees is equal to 70 times pi over 180. Which is approximately 122 radians. Now we can calculate the work done. The work W equals our torque T, 86.603 newton meters, times our angle in radians, 122 radians. This gives us a work done of approximately 105.829 joules. Remember, work is measured in joules. So, for a 70-degree turn, the work done is about 106 joules. Finally, let's calculate the power in part C. The question states the motion takes 0.5 seconds. Power is work divided by time. We take the work we just calculated, 105.829 joules, and divide it by the time 0.5 seconds. This gives us 220,658 watts. Power is measured in watts. So, the power is about 212 watts. We have now successfully calculated the work done and the power for this rotational motion. Let's move on to example 2.6. Our objective here is to work backward from a given torque to find the force. The problem states, a spanner with a length of 0.18 meters applies a torque of 60 newton meters to a nut. We need to calculate two things. First, the perpendicular force, and second, the force if it's applied at an angle of 80 degrees. Let's list the given values. The torque T is 60 newton meters, and the radius r is 0.18 meters. For part A, we need the force applied perpendicular to the spanner. We'll use our basic torque formula, T equals F times R. Let's plug in the numbers. 60 equals F times 0.18. To solve for F, we divide 60 by 0.18. The result is a force of approximately 333.333 newtons. This is the force we would need to apply at a perfect right angle to get a torque of 60 newton meters. Now for part B. This is where things get interesting. We are told the force F makes an 80-degree angle with the spanner. Remember, the torque formula TEFXR only works if F is the perpendicular force. Our total force F is not perpendicular. Let's look at the diagram. The angle between the spanner and the force is 80 degrees. The solution here is a bit tricky, so let's analyze it carefully. The solution uses the angle of 10 degrees. Where did this come from? It's the complement of the 80-degree angle. 90 minus 80 equals 10. The component of the force that is along the spanner is F cos 80. The component perpendicular to the spanner is F sin 80. The solution shows the torque is F cos 10 degrees, which is the same as F sin 80 degrees. So our torque formula becomes T equals F sin 80 times R. Let's substitute the given torque of 60. We multiply 0.985 by 0.18 to get 0.173. Now we have 60 equals F times 0.173. To find F, we divide 60 by 0.173. The result is a force of approximately 338.41 newtons. As you can see, we need to apply a slightly larger force when it's at an angle compared to when it's perfectly perpendicular to get the same torque. We have now solved the problem by determining the required force at a specific angle. Let's move on to example 2.7. In this problem, our objective is to find the load on a spindle, the work done, and the power output. The question is, a machine has a torque of 20 Newton meters at its spindle. The diameter of the spindle is 0.3 meters, and its rotational frequency is 3 revolutions per second. We need to calculate the magnitude of the load on the rope, the work done after 30 seconds, and the output power. First, let's list our given values. Torque T is 20 Newton meters. Diameter D is 0.3 meters. Rotational frequency N is 3 revolutions per second. The number of revolutions per second is often called hertz. The radius r is half the diameter, so 0.15 meters. The time t is 30 seconds, and we'll use Pe equals 3.142 as given in the solution. For part A, we need to find the load. This is the force on the rope. We'll use the torque formula, T equals force times radius. Rearranging for the load, we get load equals T over R. Plugging in our values, the load equals 20 divided by 0.1. This gives us a load of approximately 133.333 newtons. So, for a 20 Newton-meter torque and a 0.15 meter radius, the load on the rope is about 133 newtons. Now for part B, the total work done after 30 seconds. The solution breaks this into steps. Step 1 is to find the work per revolution. We use the formula W per rev equals 2 pi t. That's 2 times 3.142 times the torque, 20. This gives us approximately 125.68 joules per revolution. Step 2 is to find the work in 1 second. Since the spindle rotates 3 times per second, the work done in 1 second is 3 times the work per revolution. So, 3 times 125.68 equals approximately 377.04 joules. Step 3 is the total work in 30 seconds. We multiply the work in 1 second by 30. That's 377.04 times 30, which gives approximately 11,311.2 joules. Or, if we express it in kilojoules, it's 11.3112 kilojoules. We have now found the total work done. For part C, we need to find the output power. There are 2 ways to calculate this. Method 1 uses the formula P equals W over T. We take our total work of 11,311.2 joules and divide by the total time of 30 seconds. This gives us 377.04 watts. Method 2 uses our rotational power formula, P equals 2pnt. Plugging in the values, 2 times 3.142 times N, which is 3 times the torque T, which is 20. This also gives us 377.04 watts. Both methods yield the same result, confirming our calculations. We have successfully found the load, work done, and power for this system. We've now seen how torque causes rotational motion and how to calculate work and power. But what if the speed is changing? This leads us to our next topic, acceleration torque. Acceleration torque is the extra torque, in addition to the load torque, required to make an object spin faster or accelerate it. It's the rotational equivalent of a linear force that causes an object to accelerate, like a car speeding up. The formula for acceleration torque, T alpha, is moment of inertia I times angular acceleration alpha. Let's break down this formula. First, angular acceleration. Angular acceleration, alpha, is measured in radians per second squared. It's the rate at which an object's angular velocity changes. Next, we have the moment of inertia. The moment of inertia, I, is a measure of an object's resistance to being accelerated or decelerated. It depends on the object's mass and how that mass is distributed. Now, let's consider a situation where there's more than one torque acting on an object. For example, a motor providing torque and friction creating an opposing torque. The sum of all the torques acting on a rigid body is equal to its moment of inertia I multiplied by its angular acceleration alpha. Here, sigma t represents the sum of all torques. For example, it could be the motor torque minus the load torque and friction torque. So, in this section, we've learned how to define and calculate the acceleration torque and how to apply Newton's second law to rotational motion. Let's put the concepts of acceleration torque into practice with our final example, example 2.8. Our goal is to calculate the angular acceleration and the accelerating torque of a wheel. The problem states, a wheel with a diameter of 0.6 meters accelerates from 1 revolution per second to 25 revolutions per second in 4 seconds. If the moment of inertia is 4 units, calculate the angular acceleration and the accelerating torque. First, let's list our given values. The initial frequency N1 is 1 revolution per second. The final frequency N2 is 25 revolutions per second. The time taken t is 4 seconds. The moment of inertia I is 4 units, and we'll use pi equals 3.142. Part A asks for the angular acceleration alpha. The solution gives a formula for alpha in terms of frequency. Let's understand where this formula comes from. We start with the basic definition of angular acceleration. Alpha is the change in angular velocity, delta omega, divided by the time t. Angular velocity omega is related to frequency n by the formula omega equals 2pn, so we can substitute this in. Factoring out the 2 pi gives us the formula we're using. Alpha equals 2 pi times the change in frequency, all divided by time. This is a very useful formula when you're given frequencies instead of angular velocities. Now, let's plug in the numbers. Alpha equals 2 pi times the difference in frequencies, 25 minus 1, divided by 4 seconds. Simplifying this, we get 12 pi. Plugging in the value for pi, we find that the angular acceleration alpha is approximately 37.704 radians per second squared. We have now found the angular acceleration. For part GB, we need to calculate the accelerating torque. This is T alpha. The formula for accelerating torque is the moment of inertia I times the angular acceleration alpha. We plug in our values. I is 4, and alpha is 37.704. This gives us an accelerating torque of approximately 150.816 Newton meters. This is the torque required to cause the wheel to speed up from 1 to 25 revolutions per second. We have now successfully calculated the accelerating torque. Let's quickly recap what we've covered today. First, we defined torque, the turning effect of a force, and learned how to calculate it as the perpendicular force times the radius. We saw how to resolve forces into their perpendicular components. Second, we derived the formula for work done by torque over an angle theta, W equals T dot theta. We also established the crucial step of converting degrees to radians. Third, we explored power in rotational motion using P equals W over T, and derived the rotational power formula, P equals 2 pi nt, where n is the frequency. Finally, we introduced acceleration torque, which causes a change in rotational speed, and its formula, T alpha equals moment of inertia E times angular acceleration alpha. You are now equipped to define, calculate, and apply these key concepts of torque, work, and power to various rotational problems. Thank you for joining us today. Subscribe for more tutorials from Math Zone African Motives.